Problem 3 is a air conditioning problem. As you see on the screen here, the first part is worth 20 points. And the problem statement is that during a air conditioning process, 300 cubic feet per minute of return air is mixed with 120 cubic feet per minute of outside air. The return air is at 75 degrees Fahrenheit and a relative humidity of 60%. The summer outside air is at 95% Fahrenheit, 95 degrees Fahrenheit, and a wet bulb temperature of 85. For adiabatic mixing process with constant pressure of 1 atmosphere for both of the streams, we are to determine the temperature and the humidity ratio for the mixed moist air. And so in this particular problem, it's fairly straightforward, 2 streams coming together and ending up with a final stream and determining what the temperature and humidity ratio is for that. The next problem, which will follow on, is then taking that stream and causing it to go through a conditioning unit such that the temperature at the exit of going through this conditioning stream is at 60 degrees Fahrenheit and at a relative humidity of 75%. And so in the solution of problem 3, I'm going to go ahead and also identify an additional state, a fourth state, that corresponds to the answer to the 10-point file problem number 4. I then will have a separate video where I talk about the extra credit. So with that in mind, we can now go to our software. Oh, I gotta find it here. Okay, so this is a flowing HVAC problem. And so we see down here, it's a specific type of process, a psychometric process. And so we're going to select that. We will then begin by looking at what state 1 is. And state 1 has a volume flow rate that's equal to, well, we're going to do everything in English, and so I've selected the English units. And so the volumetric flow rate is 300 CFM, cubic feet per minute. As we see here, we only have the capability of putting in cubic feet per second. And so as I indicated, one needs to do the math and take 300 divided by 60 and come up with 5 cubic feet per minute for the flow rate. Again, putting in an expression 300 over 60 does not seem to work. Okay, so we have our volumetric flow rate. We have our, because everything's coming in at 1 atmosphere. If I turn this over to 1 atmosphere, you see that it defaults to 1 atmosphere. That's close to 1 atmosphere. And then we are told that this state 1 will be the return air, and that is at 75 degrees Fahrenheit. With a relative humidity of 60%. So we have to make sure that we select the percentage. Okay, so with those two, actually the 3 thermodynamic properties given, we see that we have the amount of dry air. We also have the amount of moisture that's flowing through in that particular stream. We now go to state 2, which is the outside air. And what we know about the outside air, it also is at an atmospheric pressure of 1. it has a volume flow rate of 120 divided by 6, or 2 cubic feet per second. And we also know that it is at a relatively warm 95 degrees and a wet bulb of 85. And so we come over to here. It's not the dew point, but rather the wet bulb temperature. And so with those two plus the third pressure, we are able to determine the state of the outside air that's being brought into the system at a certain amount. So we see this is how much dry air, and this is how much moisture is coming in. We compare that to state 1. State 1, we had this amount of dry air, and we had this amount of moisture. And so we're now ready for state 3, which is the mix, the adiabatic mixed component. And so in this particular case, we know that the mass of the dry air of 1 plus the mass of the dry air of 2 is what we have for the dry air component. And likewise, we say the same thing for the mass of the dry air of the vapor plus the mass of the vapor at state 2. So we have the vapor as well as the air coming together, and the volume flow rate does not add up. Okay. What else do we know about this process? Well, we know that the process is an adiabatic mixing process. And so when we go to our device panel, we can specify that. Now, we could have, if we wanted to, we could have said that the total flowing energy, this J3, we could have performed our first law adding J1 and J2 with the corresponding mass flows of dry air, but we're going to let the device panel do that for us. We have the incoming return air, which is state 1, combining with the state 2 outside air, forming then the mixed condition, which is the moist air there. No work, as well as no heat transfer. And so basically an adiabatic process occurring, we do a super calculate, we go back to the state panel, and we see then that it performed the calculation as to the energy flow being conserved, and it was then able to determine that the output condition or the mixing condition has a temperature that's equal to 80.57 and a humidity ratio omega of 0.0146, usually seen in terms of grains or however you want to observe it. And so that is the humidity ratio associated with the mixed condition. So that is the answer to the problem, or the problem number 3, the first part of the air conditioning process. And so as I said, we're going to go ahead and take this stream of air and moisture and go through the conditioning unit. And so as it goes through the conditioning unit, a couple of things are going to happen. One thing is that there is going to be moisture that is removed, and the air is going to come out at a different condition. And so we're going to go ahead and specify that state 4 is going to be coming out of the conditioning unit. And so we are told in problem number 4 that it comes out at 60 degrees at a lower temperature, so it is being cooled, and it's also coming out at a relative humidity of 75%. Now, what we do know in this particular problem is that the mass of dry air does not change between 3 and 4. The total amount, which was calculated in state 3, is equal to the total amount of dry air at state 4. And so for this amount of dry air at this temperature and at this overall pressure, at this relative humidity, we now see that the amount of vapor is 0.0041. And what has happened is whatever these two, when I added these two together, which was the vapor that was in the return air, 0.004, the vapor that was in the outside air, which was 0.0033, that's 0.0073, and that was the total, and now it's gone down to 0.0041. So a certain amount of mass of vapor has been condensed. And so in order to include that in our energy balance to determine how much energy we had to remove, we do have to determine a fifth state. And the fifth state is going to be the state of the condensate. And so I select states 5. I select the fact that it's water as a phase change substance. And I'm going to go ahead and say that the temperature of that water coming out is at the temperature of the exit stream. So I'm going to go ahead and say that that's at temperature 4. Okay, now we'll go ahead and say that it's at 1 atmosphere of pressure. Oops. And so now at that 60 degrees and at this 1 atmosphere of pressure, it is liquid, subcooled liquid water. This is the conditions associated. We also need to identify the amount of mass there is, the mass flow rate in pounds per second. And so we know that it's m dot vapor that was at the 3 condition, that we then subtract the mass of the vapor at the 4 condition. So 3 was after it mixed, 4 was the final cool down and dehumidified section. And so that is our mass flow rate of the liquid. So now we're ready, since we now have state 4 and we also have state 5. We're now able to set up a second device panel, and this device panel is going to be the state 3 coming in. This is just the device that was called the conditioning unit. State 3 coming out, state 4 coming out, along with state 5. So we see that it's moist air plus the water vapor, and that's the condensate. And then there's no work, and this then should calculate for us. When we do a super calculate, we should now be able to go back to the device panel, and we can now determine that during this particular process, going from 3 to 4 with water coming out, we then see that it required minus, or heat coming out of the system, of 1.789 tons of refrigeration. Okay, so that then, for this, that is the cooling capacity in tons. As we went through the conditioning unit and came out with the relative humidity and a cool stream, and also the condensate came out.